Let's review how we would use the normal distribution to make a prediction about how many defects or defectives a process would be creating over time. We're basically going to apply the empirical rule that looks at the probability of data being more than a certain distance from the mean under the normal distribution. So here's a sample of data that I took. I took starting at 7 o'clock in the morning, every 18 minutes. I took an observation from my basic process as I went through, and in each of those observations, I determined 6 different values that I would average to try to take the value. Later in statistics, you're going to learn the central limit theorem, and that's going to explain why we're taking 6 observations to come up with one. We do our control charts, but for now, that's beyond our current lesson. So I've got all this data that I want to use, and I'd like to know what is the defect rate of the process that I'm measuring when I take these measures. The basic specification for the process is that whatever it is I'm measuring should be 2 plus or minus 1. So let's just say it's millimeters. 2 millimeters plus or minus 1 is the target and tolerance for what I've got going on. So I want to be able to measure this data. So the first question is this data reasonably normal? I mean, does it map to a normal distribution? And we could, in fact, later precisely map and determine how closely it matches the normal distribution. But early in the discussion, we're not going to get that involved. We basically just want to display our data much like we did in the first chapter of statistics in terms of, is there a visual display we can use that will determine the basic shape of the data and ensure that the data is more or less normal as we go on. So one of the ways I can do that is I can take the descriptive statistics for those data points. Here it is if I run it through Excel. The mean is 1.79 and the median is 1.80. So the mean and median are close enough together that it probably is more or less a bell curve as I go through. In a perfect normal distribution, they would be equal, but I rarely see data that's perfectly normally distributed. So I know from the mean and the median that they're close enough together that I'm probably looking at some kind of a bell curve. The kurtosis of my data is negative, the excess kurtosis, so it's a little flatter than I would expect from a normal distribution in a bell curve. It's not quite a bell curve, it's going to be kind of a low bell curve, if you will. And the skewness is slightly positive, but only slightly in these units. So my tail to the right is going to be a little bigger than my tail to the left as I go through. My data is probably going to be more or less normal. So I could right now kind of declare the data is normal enough as I go, but I should probably create a visual display as I do. So if I take maybe 7 bins out of this as I go through, I've got 144 data points. So if I take 7 bins and divide the data up into bins of roughly half a millimeter each, these will basically be my bin boundaries, and I can run them through the histogram builder here in Excel, and I can get a visual display of the data. The visual display shows that the data is indeed flatter than I expect. I don't have the big bulging center. I've got a lot more data to the right or to the left. So my data is kind of all over, but judging from that mean and median, the low skewness, the slightly flattened kurtosis, I'd be willing to declare this data is normal enough to continue with my analysis. Now, normal enough will be subjective. If this were a high-risk process, I might be more concerned and maybe go collect more samples. If it's a low-risk process, I'll be perfectly happy. So the decision-making you make in engineering is based on your level of risk in the project you're trying to manage. Either way, you apply the statistical rules the same way. So if I'm pretty much happy that I've got data that's normal enough for my analysis, I'm going to begin my analysis against the normal distribution to come up with the probability of this process producing defects. I start with the mean and the standard deviation. That's really my 2 factors that truly describe my data set. So I've got a mean of 1.79, a standard deviation of 0.95 in my data. So the question is, at that rate, how many of the widgets this process creates, if you will be outside those plus and minus 1 tolerance as I go through. So I need to know what that tolerance is. The target was 2. The tolerance is plus or minus 1. So I do know that going in, which really means I can define the upper and lower specifications for my data. The lower specification is a 1 rather, 2 minus the 1, and the upper specification is a 2 plus the 1. So that's pretty intuitive. I want my data to fall between 1 and 3. So anything that falls in my observations between 1 and 3 would not be considered a defective. Anything that falls outside is. So I need to know how far are those boundaries from the mean. So I'm going to calculate a delta, or a deviation, if you will. The deviation is simply the spec limit, in this case the 1 in column D, minus the 1.79 mean, which means that the deviation here, the specification is 0.7917 to the left of my mean. So 1 is to the left of the mean. The mean is inside the spec limits as I would expect, so I know how far in these units, millimeters if that's your example. I would do the same thing on the upper side. I would take the 3 minus the 1.79 to determine that the 3 specification limit is 1.2 above the 1.79. The positive value tells me it's above the mean. The negative value told me it's below the mean. And that shouldn't surprise you that the mean of the distribution is somehow between the lower and the upper specification limits. But I can't calculate the probability of that happening because I don't have probability data for a curve with a mean of 1.79 and a standard deviation of 0.95. So what I need to know is how much these deviations are in terms of the standard deviation. If I treat the standard deviation as my unit of measure, the resulting factor I'll have is not in millimeters like these values are, but it will be a factor called z. The z factor is how far the deviation is in terms of standard deviations. So I take my deviation, my delta, and I divide it by the standard deviation number in B2, and that gives me a measure in standard deviations. So while the lower limit was to the left 0.79 millimeters from the mean, that limit is 0.829 standard deviations from the mean. That's the number I really want to know. On the upper side, I do the same arithmetic. I divide the 1.2 deviation by the standard deviation, and now I know that the upper limit is to the right of the mean by 1.2 standard deviations. If that sounds familiar, we learned in the empirical rule that if we know the number of standard deviations we are from the mean under the standard normal curve, we can predict the probability. That's exactly what we can do now, is predict the probability that data will fall outside of these limits. Okay, so we can do our probability. We have to do each one separately. I'm using an Excel function here to go look up the probability of the normal standard deviation distribution at negative 0.829 standard deviations. The norms dist function gives me the area under the curve. It integrates the normal distribution from negative infinity up to the value, the z value that I give it. So from the entire left tail up to 0.829 is what I'll return with this deviation. That's 20.4% of the curve. Okay, so the norms dist function, you want to learn that in Excel, and based on your version of Excel, your syntax might be a little different. But if I know the standard deviation, negative 0.829, I can predict that 20.4% of my observations will fall in that curve. On the high side, I've got to tweak it a little. I'm still using the norms dist function, but notice I'm subtracting it from 1 because I want to know the probability of being to the right of 1.265 standard deviations above the mean. And the norms dist function doesn't give me that. It integrates the normal curve from negative infinity up to my z value. So in essence, the norms dist function is giving me everything to the left of 1.265, and I want everything to the right of 1.265, and I can do that by subtracting that probability from 1. So on the high side, I've got a 10.3% defect rate. On the low side, 20.4. On the high side, 10.3. I add that data together, and I get 30.6%. So I know I'm reasonably ensured that 30.6% is the expected defect rate of this process. That requires me to acknowledge that the data wasn't perfectly normal, so it's probably going to be pretty close to 30.6, but probably not exactly 30.6. It also tells me I have to presume that nothing unusual happened during the few hours that I was measuring the process, that I actually measured one process all day and that nothing extraordinary happened. But if those assumptions hold, I can predict that this process will produce 30.6% defects over the long haul as it executes itself.